Welcome back. In this video, we're going to learn how to find the equivalent resistor in a complex circuit of resistors. Whether the resistors are connected in series, parallel, or a combination of both, we'll walk through different configurations, step by step, breaking down the resistors into simpler forms, so that we can calculate the overall equivalent resistance. But before we dive into that, let's first get a clear understanding of Ohm's law. Ohm's law states that the voltage across a conductor is directly proportional to the current flowing through it, provided all physical conditions and temperatures remain constant. This means that, if we increase the voltage, the current also increases proportionally, assuming the resistance remains constant. Mathematically, this current-voltage relationship is expressed as follows, where V is the voltage measured in volts, and I is the current measured in amperes. In the equation, the constant of proportionality, R, is called resistance, and has units of ohms. The same formula can be rewritten to calculate the resistance as follows. This form of expression will be important as we progress in this video to find the equivalent resistance in different configurations of resistors. So, let's get started. In this section, we are going to find the equivalent resistor for a network of parallel resistors. Resistors R1, R2, R3, and R4 are connected in parallel to a voltage source V, with one side of the voltage source connected to the ground. By connecting one side to the ground, we ensure that the voltage at this point is zero, which simplifies the circuit analysis. I recommend following this best practice when analyzing circuit diagrams, as it provides a clear reference point. The voltage along the conductor, connected to the ground, remains zero. On the other hand, the other end of the voltage source is at V volts, representing the voltage of the source. Since points A1, B1, C1, D1, and E1 form a single conductor with zero resistance, the voltage along this line remains constant, and equal to the source voltage V. When resistors are connected in parallel, the voltage across each resistor is the same as the source voltage V, but the total current is divided among the parallel branches. The current through each resistor depends on its individual resistance, and we can use Ohm's law to express the relationship between voltage, current, and resistance. The current through each resistor can be expressed as follows. The sum of the currents through each resistor is equal to the total current flowing from the voltage source. In other words, the total current I is the sum of the individual currents through each resistor in the parallel network. We can substitute the corresponding expressions for the currents through each resistor into the equation, which gives us an expression for the total current I, in terms of the voltage V, and the resistances R1, R2, R3 and R4. Now we can factor out the voltage V. Simplifying this equation gives us the ratio of current to voltage for the entire circuit. What you see on the screen is the same circuit, but with one equivalent resistor, replacing the parallel resistors. This equivalent resistor, R sub EQ, must maintain the same current to voltage ratio as the original configuration, to truly represent the parallel network. This gives us a single equivalent resistor, that could replace the entire parallel network, while maintaining the same voltage and current characteristics as the original circuit. So, what you need to take away from this expression is that, when you have a number of resistors connected in parallel, the sum of the reciprocals of the individual resistances is equal to the reciprocal of the equivalent resistor. This concept is key to simplifying complex circuits with parallel resistors, and allows you to replace the parallel network with a single equivalent resistor that behaves the same way electrically. Next, we will examine the equivalent resistance of a set of resistors connected in series. In this diagram, we have 4 resistors, each with different values, connected in series with a voltage source of V volts. Unlike the previous parallel circuit, where the current was divided among branches, in a series circuit, the current flows through a single closed loop, passing through all 4 resistors and the voltage source. Since there are no branches in a series circuit, the same current flows through each resistor and the voltage source continuously. The total resistance in a series circuit is simply the sum of the individual resistances, and this is what we'll explore next. When current flows through a resistor, according to Ohm's law, there is a voltage drop across the resistor. This voltage drop across each resistor can be described in terms of the current flowing through it and the resistor's value. The sum of the individual voltage drops from each resistor adds up to match the voltage provided by the source. We can replace the voltage drop across each resistor in this equation with their respective expressions, resulting in an equation that incorporates each resistor and the current flowing through the circuit. Next, we can factor out the current I from the equation. By simplifying the equation in this way, we can express it as the ratio of total voltage to current for the entire circuit. What you see on the screen is the same circuit diagram, but now the series resistors have been replaced with a single equivalent resistor. Just like we did earlier, let's identify the equivalent resistance by expressing the resistance as the ratio of voltage to current. This ratio must match the original circuit with the series resistors. Only then can we replace the series resistors with a single equivalent resistor that behaves the same way electrically. Finally, we can express the equivalent resistance for this series configuration. In other words, the total resistance is simply the sum of the individual resistances, which is equivalent to a single resistor that would produce the same effect in the circuit. This simplification allows us to model the system more easily without altering its physical behavior. I hope everything we've covered so far is clear. Let's now look at an example to help us better understand what we've been discussing. What you see on the screen is a circuit with a combination of series and parallel resistors. Our goal is to find the equivalent resistor that can be placed between nodes A and B. First, we need to identify any resistors that are connected in either series or parallel within the circuit. Once we've found these, we can replace them with a single equivalent resistor. These two parallel resistors are easy to spot right away. To simplify them, we can calculate the equivalent resistance for the pair using the formula for parallel resistors. The equivalent resistor that replaces the two parallel resistors is 4 ohms. Since both resistors have the same value, the equivalent resistance is half the value of one of them. This rule applies when you have two equal resistors in parallel. However, if you have multiple resistors of the same value in parallel, you can simplify the process by dividing the value of one resistor by the number of resistors in parallel. For example, if you have 3 equal resistors in parallel, the equivalent resistance would be 1/3 the value of one resistor. Remembering this shortcut can help you simplify circuits much faster when dealing with equal resistors in parallel. Next, we can easily spot these 3 resistors connected in series. To find the equivalent resistance of resistors in series, we simply add their values together. In this case, the sum of the 3 resistors is 12 ohms. We can now replace these 3 resistors with a single 12 ohm resistor, further simplifying the circuit. I am sure you've already guessed what's next. We'll replace these 2 parallel resistors. But instead of using the equation to calculate the equivalent resistance, we'll apply a shortcut. When there are 2 equal resistors in parallel, you can replace them with a single resistor that has a value of half of one of the resistors. This shortcut helps simplify the circuit much faster, without needing to use the full formula. We can calculate the value of the equivalent resistor for the 2 parallel resistors as 6 ohms, using our shortcut. Now, let's go ahead and replace those 2 resistors with a single 6 ohm resistor, simplifying the circuit further. With this replacement, we're one step closer to finding the total equivalent resistance between nodes A and B. These 3 resistors are connected in series. To calculate the equivalent resistance, we simply add the values of the 3 resistors together. This gives us the equivalent resistance between nodes A and B as 10 ohms. This final step simplifies the circuit, showing that the entire network of resistors between A and B can be replaced with a single 10 ohm resistor. I hope the explanation was clear. Now, let's move on to another example to explore a new concept. This concept is incredibly useful, and will come in handy when simplifying complex circuit diagrams. Let's dive in and see how it works. The circuit diagram here consists of two resistors in series and two parallel branches. The entire resistor network is connected to a 12-volt voltage source. Our goal is to find the voltages at V1 and V2. We can indeed use Kirchhoff's laws to find the voltages at V1 and V2. However, let's take a simplified approach by first calculating the equivalent resistance, and then the total current I, that flows through the circuit. Once we have the current through each branch, we can use this information to determine the voltages at V1 and V2 by applying the voltage drop across the resistors in each branch. We can easily identify the two sets of resistors in series. The equivalent resistance of resistors connected in series is the sum of their individual resistances. The first set of resistors adds up to 60 ohms, and the second set totals 30 ohms. We can then replace these two sets of resistors with their respective equivalent resistances of 60 and 30 ohms. These two resistors in parallel have different values. We can't use the shortcut method for equal resistors. Instead, we apply the formula for finding the equivalent resistance of two resistors in parallel, which involves multiplying their values and dividing the result by their sum. After performing the calculation, the equivalent resistance comes out to be 20 ohms. By replacing the two resistors with a single 20 ohm resistor, we simplify the circuit, making it easier to determine the total current. To find the total current, we can use Ohm's law, which gives a total current of 0.6 amperes. Let's return to the initial circuit. Now that we've determined the total current flowing through the circuit as 0.6 amperes, our next step is to figure out how much current flows through each branch. Since the branches are in parallel, the voltage across both branches is the same, but the current will divide based on the resistance of each branch. Let's apply Ohm's law to find the currents I1 and I2 in each branch. Now, observe that the total current is equal to the sum of the currents in both branches. This is no coincidence, it's a direct application of Kirchhoff's current law, KCL, which states that the sum of the currents entering a node, in this case, node P, is equal to the sum of the currents leaving it. While we calculated the current in each branch using Ohm's law, Kirchhoff's current law also allows us to determine the total current, without needing to find the equivalent resistor first. Essentially, if we can determine the current in each branch, we can apply KCL to calculate the total current of the circuit. If we already know the total current and the voltage, we can easily calculate the equivalent resistance without simplifying the circuit, as demonstrated here. We explored two methods for calculating the equivalent resistor. In the first method, we simplified the circuit step by step, combining series and parallel resistors to find the equivalent resistance. In the second method, we applied Kirchhoff's current law, KCL, to calculate the total current in the circuit, and then used Ohm's law to determine the total resistance. Both approaches lead to the same result, but each offers a different perspective on analyzing complex circuits. Alright. Now that we know the current flowing through each branch, we can calculate the voltage drop across each resistor, using Ohm's law. For each resistor in both branches, we'll simply multiply the current in the branch, I1, or I2, by the corresponding resistance, to determine the voltage drop across that resistor. We can calculate the voltage drop across resistor R1, and R2 is 4 volts, while the voltage drop across resistors R3 and R4 comes out to be 8 volts. Now if you observe closely, the sum of the voltage drops along both the inner and outer loops is the same and equal to the source voltage. This is no coincidence, it's a principle known as Kirchhoff's voltage law, KVL. KVL states that the sum of the voltage drops around any closed loop in a circuit is equal to the algebraic sum of the source voltages in that loop. Essentially, this law reflects the conservation of energy, meaning all the voltage provided by the source is fully used by the components within the loop. I'm sure you've noticed that the voltage drop across resistors R1 and R2 is the same, and similarly, the voltage drop across resistors R3 and R4 is also identical, regardless of the differences in resistor values and the current flowing through the branches. This phenomenon is only possible if the ratio of R1 to R3 is equal to the ratio of R2 to R4. If this condition is not satisfied, the relationship will not hold. This principle is known as the Wheatstone bridge formula, and it is frequently used for measuring unknown resistances. Now, let's return to the task of finding the voltages V1 and V2. Remember, voltage is always measured between 2 points, so when we refer to V1 and V2, we're really talking about the voltage at those points relative to the reference point, which in this case, is where we have identified zero voltage. Since we've already calculated the voltage drop across resistors R3 and R4 as 8 volts, we can immediately determine that the voltage at both V1 and V2 is 8 volts. What's important to understand is the advantage of identifying two nodes with equal voltages in a circuit. When two nodes have the same voltage, they are effectively at the same electrical potential, meaning there is no voltage difference between them. This insight allows us to simplify circuit diagrams without changing their fundamental behavior. By recognizing such nodes, we can make changes, such as combining or removing certain components between those nodes, which helps to simplify the analysis of complex circuits. Let's explore how this concept can be applied to streamline circuit analysis. In this circuit, which is quite similar to the previous example, all resistors are identical, and there's a resistor between nodes K and L. In the previous case, we concluded that the voltage at K equals the voltage at L, which holds true in this circuit as well. However, in more complex circuits, where determining the voltages isn't as straightforward, the first step is to check for any symmetry. Here, if you draw a line across points A and B, the circuit divides into two symmetrical parts. The resistors on the left are identical to those on the right, and the resistor between K and L can be viewed as split between the two halves. To simplify, we trace the circuit starting from point A. As we move, if we encounter a resistor, we cross to the other side and assign a voltage. If we come to a node with branches, we check if the branches have the same number of resistors in series on both sides. In this diagram, there are two branches with identical resistors on either side of the dividing line. As we continue along the resistors, we eventually reach a node with equal voltages. Mark these voltages as V1. Why did we say that the voltages at these two nodes are equal? It's because the current flowing through the two branches is identical, thanks to the symmetry of the circuit. As a result, the voltage drop across the identical resistors in each branch is the same. This leads us to assign the same voltage to both nodes, since there's no difference in the electrical potential at those points. Since the voltage across the resistor between nodes K and L is equal, no current flows through resistor R5. Therefore, we have two options: either remove the resistor from the circuit entirely, or connect the two nodes with a conductor, effectively short-circuiting them without affecting the circuit's overall behavior. We will remove the resistor R5, and continue tracing along the two parallel paths, stopping when we reach the end of the resistors. This process simplifies the circuit by reducing the number of resistors, without altering its characteristics, making it easier to clearly identify the series and parallel resistors. To calculate the equivalent resistance of the circuit, we start by simplifying the resistors that are connected in series. For resistors in series, their equivalent resistance is determined by adding their individual resistances together. Once the series resistors are replaced with their combined resistance, we then focus on the resistors in parallel. By applying the general formula for resistors in parallel, we can compute their combined resistance. After completing these steps, the circuit is simplified further, reducing it to a single equivalent resistor of 10 ohms. Now we should also verify whether we obtain the same equivalent resistance when nodes K and L are short-circuited. With the connection established between nodes K and L, resistors R1 and R2, as well as R3 and R4, are now in parallel. By applying the standard formula for parallel resistors, we calculate the equivalent resistance for each pair. After solving, the equivalent resistance for both R1 and R2 comes out to be 5 ohms. Repeating the same calculation for the parallel combination of R3 and R4 also results in an equivalent resistance of 5 ohms. These two 5 ohm resistors are then in series. When resistors are in series, we simply add their values to determine the total resistance. The combined resistance is 10 ohms, which confirms the result we derived earlier. In summary, when dealing with complex circuits, the first step is to check for symmetry. If symmetry is present, identify the branches on either side of the symmetrical line, and trace through the circuit to locate equipotential nodes. When two or more nodes have the same potential, no current will flow through a resistor or conductor between them, as current flow requires a potential difference. As a result, you can either remove the resistor between these equipotential nodes, or add a conductor without changing the overall behavior of the circuit. At this point, if there are resistors in parallel, or in series, replace them with their equivalent resistances. After making these adjustments, continue tracing through the circuit, until you encounter another set of resistors. By following this systematic approach, the circuit is progressively simplified, making it easier to calculate the final equivalent resistance. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. Let's apply the principles we've discussed to find the equivalent resistance between points A and B in this circuit, where all the resistors are identical. The first step is to identify whether there is any symmetry in the circuit. This circuit, with identical resistors, is symmetrical about a central axis. It's important to remember that current flow in symmetrical branches is identical. Recognizing this symmetry will help us locate the equipotential nodes more easily. Now, let's trace the circuit, starting from the positive end of the source, and move along until we encounter a junction or resistor. We first reach a junction. At this point, we need to verify if the branches diverging from this junction are symmetrical with respect to the axis. We should only select the branches that exhibit symmetry along the central axis. Once the symmetrical branches are identified, we can trace along them simultaneously until we encounter another junction or resistor. After crossing over to the other side of the resistor, we observe that since the two resistors are identical, and the current flowing through each branch is the same, the voltage across both resistors must be equal. This means that the voltage at node P is equal to the voltage at node R. Consequently, there is no voltage difference across the resistor connected between nodes P and R, as both nodes are at the same potential. With no voltage difference, no current flows through this resistor. We now have two options: either remove the resistor from the circuit, or connect the two nodes with a conductor. Connecting the nodes will make it easier to further simplify the circuit. At this point, we have 4 resistors left to deal with. The circuit remains symmetrical about the axis between nodes A and B. Because of this symmetry, the current flowing through the resistors connected between nodes PQ and RS must be the same. We can also assume that the current flowing through the resistors between nodes P and S, as well as nodes R and Q, is the same. While it might not be immediately obvious that the magnitudes of the currents are identical, this will become clear later. For now, let's focus on the voltage drop across the resistors between nodes PQ and RS. Since the same current flows through both resistors, the voltage drop across them must be the same. This implies that the voltage at nodes Q and S is also the same, meaning no voltage difference exists across the resistor connected between these nodes. With no voltage difference across the resistor between nodes Q and S, no current will flow through it. As we did earlier, we can replace this resistor with a conductor. Once this adjustment is made, the remaining circuit can be rearranged to reveal a clearer arrangement of parallel and series components, simplifying the process of calculating the equivalent resistance. Now, we have three sets of parallel resistors. The equivalent resistances of these parallel resistor sets can be placed in series, as shown. Earlier, we mentioned that for identical resistors in parallel, the equivalent resistance can be calculated using a shortcut. Simply take the value of one resistor and divide it by the number of resistors in parallel. We will use this method to calculate the equivalent resistance of the three sets of parallel resistors in the circuit. In the first section, we have two parallel resistors, each with a value of R. Using the shortcut, the equivalent resistance of the first section is half of the original resistance. In the second section, there are four resistors connected in parallel, each with the same resistance value, R. The equivalent resistance of this section is 1/4 of the value of a single resistor, meaning it's equal to or divided by 4. In the third section, just like in the first section, there are two resistors connected in parallel. Therefore, the equivalent resistance of this section is also half of the resistance of a single resistor, meaning it's R divided by 2. These three resistors are connected in series, so to find the equivalent resistance, we simply add the resistance values of all three resistors together. This results in an equivalent resistance of 5 times the value of a single resistor, divided by 4. I hope this explanation was clear, and I trust you recognize the importance of identifying symmetry in a circuit. The current flowing through symmetrical branches is indeed the same, which helps in pinpointing equipotential nodes. Once you've identified these equipotential nodes, you can either combine them, or remove any components connected between them, simplifying the analysis of the circuit. This approach not only streamlines the calculation of equivalent resistances, but also enhances your understanding of how circuits function as a whole. Let's take a look at another example, which will be the last one we go through in this video. I will upload a few more examples later. In this example, as in the previous ones, we need to find the equivalent resistance between the nodes X and Y. However, unlike the earlier circuits, the symmetry in this circuit may not be immediately obvious, given how it is drawn. In such cases, it can be helpful to redraw the circuit, to better identify the symmetry. Now that we've rearranged it, I think it's clear that this is what we call a Wheatstone bridge. You may recall the condition we discussed in the previous section, when the ratio of the resistances in one pair of branches matches the ratio of the other pair, no current flows through the middle resistor. In this circuit, that middle resistor is the 6 ohm resistor. This condition implies that we can disregard the 6 ohm resistor, simplifying the circuit. Now we can apply the series and parallel resistor formulas to calculate the equivalent resistance between nodes X and Y. The resistors P and Q, as well as R and S, are connected in series. To find the equivalent resistance of series resistors, we simply add their values. Next, the 6 ohm and 12 ohm resistors are in parallel. To find the equivalent resistance of two resistors in parallel, we use the following formula. Finally, we obtain 4 ohms as the equivalent resistance between points X and Y. Thank you for watching until the end of the video. I hope this discussion has shed some light on how to find the equivalent resistance of networks of resistors. I'll be uploading more content related to similar topics So be sure to stay connected by pressing the bell icon to receive notifications when new videos are uploaded. If you haven't subscribed to this channel yet, please do so, it would be a great encouragement for me. If you enjoyed this video, please give it a thumbs up. Until we meet again in another video, stay safe, and goodbye.